Hello, I'm Michelle Crummell, and in this lesson we're going to look at the limiting value of the Riemann sum and use that to define the definite integral. Let's take a few minutes to talk about notation. So in this graph we see that we have a function. We're going to call the function f of x. And we have a right Riemann sum. So our interval, which begins here at A and ends here at B, right? The interval goes from A to B. The interval is broken up into subintervals. So we start at A, and then the end of our first subinterval is x sub 1. The end of our second subinterval, x sub 2, and so on until we get to the end, where we're at B, which is also going to be x sub n. Write an expression for the number of rectangles. Well, when we're on the right side of the first rectangle, that is x sub 1. The right side of the second rectangle is x sub 2, x sub 3, and so on. And so these subscripts, the 1, the 2, the 3, in effect, are counting how many rectangles we have. When we're at x sub 1, we're at the edge of the first rectangle. If I were at x sub 7, I would be at the edge of the right edge of the 7th rectangle. So at x sub k, I have k rectangles, and by the time I'm at the end, x sub n is the nth rectangle. So how many rectangles do we have? N. And these subscripts, x sub 1, sub 2, sub 3, sub k, and so on, are counters. Number 2, write an expression for the width of each rectangle. There are different ways we can express the width, and we have purposefully set this up so that the width of each rectangle is the same. We are dividing our interval from A to B into subintervals of equal width. Okay, so the width of this first rectangle right here, it is a horizontal distance, and to calculate horizontal distance, you take the right x value minus the left x value. So it is x sub 1 minus a. But that's the same width as the next rectangle, which is x sub 2 minus x sub 1. And that's the same width as the next subinterval there, x sub 3 minus x sub 2, and so on. I could say that the width of each interval is x sub k minus the one that comes right before that then would be x sub k minus 1. It would have the subscript 1 less than it. Or if I'm at the end here, I could say x sub n minus x sub n minus 1. So lots of different ways we can express the width of each rectangle. These are all equal to each other, and so we can simplify this notation. It doesn't matter which rectangle in particular we're thinking about. We know that the width is always just going to be delta x. We don't need a subscript there because all of the widths are the same. So we have n rectangles, and the width of each rectangle is delta x. Now there's another way that we can express that. If we have n rectangles from A to B, then the width of each rectangle is just b minus a, the width of the entire interval, divided by n, the number of intervals. The height of each rectangle, now this varies, right? The height of this first rectangle is not the same as the height of this next rectangle, which is not the same as the height of this next rectangle. So the height, it is a right Riemann sum, so we're determining the height of each rectangle looking at the right endpoint of the subinterval. So here the height is f of x sub 1. For the second rectangle, it's f of x sub 2. For the next, it's f of x sub 3, and so on. So in general, the best we can say is that it's f of x sub, and here k represents like our general case. So f of x sub k. F of x sub k is going to give us the height of the kth rectangle. Another thing I should mention, that this diagram is supposed to be generic. It could represent any number of rectangles. Literally, you can count and see that there are 10. Is it 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 rectangles there, but they're not really supposed to be 10 rectangles. There was just no good way to draw it with omitting some rectangles in between, right? If I made the width smaller, then we're going to have many more. We could have many more rectangles. This is just sort of to help us organize our thinking. Now write an expression for the area of each rectangle. Well, the area of each rectangle is its width times its height. Its width is the width of the subinterval, or as we said, the delta x. And then the height is the f of x sub k. So this would represent the area of each rectangle. An expression for the total area, so now we want to add up all of these individual areas for each rectangle. We want to add them up, and to do that, in an abbreviated notation, we're going to go with sigma notation. So this capital Greek letter sigma is what we use to represent a summation. We are summing the areas of the triangles. So delta x, f of x sub k, and then we are summing for all values of k, all possible values of k. Remember, k is a counter. If k is 1, we're at the first rectangle. If k is 5, we're at the fifth rectangle. So we want to add up the areas of all the rectangles for any values of k, starting with k equals 1 and stopping when we get to the end when k equals n. So we're going from k equals 1 to k equals n. And this will find the sum, or the total area, of all of the rectangles. Now let's take a closer look at our x values, which are the right endpoints of each of our subintervals. So x sub 1, this value right here, that would be a plus this distance right here, which is delta x. So a plus delta x would give us x sub 1. If I wanted x sub 2, I could also start at a, but now I have to go over two subintervals. So I add delta x plus delta x. So it's a plus 2 delta x. If I want to get all the way out to the kth rectangle, then I have to add delta x a bunch of times. How many times? K times, to get to the kth, the right endpoint of the kth subinterval. So x sub 3 is just a plus 3 delta. Oh, I did not write that correctly. Let's fix that. Plus 2 delta x. There we go. Plus 3 delta x. And then to get to the kth x value, it's going to be a plus k times delta x. We have to add delta x k times from the starting point, which is a, to get to the right endpoint of the kth subinterval. So we've just broken down the notation that we're going to be using. If f is a continuous function defined on a closed interval from a to b, so a being the left endpoint of the interval, b being the right endpoint of the interval, the interval, closed interval from a to b, is divided into n equal subintervals of width delta x. And we've also seen that we can re-express delta x as b minus a over n. b minus a is the width of the entire interval. We divide that by n, the number of subintervals, or the number of rectangles, and we get the width of each one. We also saw that we had this expression for x sub k. To get to the right endpoint of the kth interval, it's going to be a, the starting point of the interval, plus delta x times k. Now we can define this expression here, the sum, f of x sub k times delta x, which we said, let me highlight and break this down. So this part right here is the total area of all of the rectangles. So total area of all rectangles in the right Riemann sum. Then we are taking the limit as n approaches infinity. So think about what that's going to accomplish. If we are letting n approach infinity, n represents the number of subintervals, or the number of rectangles. And we're going to let that value of n approach infinity. So if we have infinitely many rectangles, or infinitely many subintervals, how wide is each one? Well, each one is going to have a width of, it's going to be approaching 0. It's going to be approaching a width of 0. So you have these super, super skinny subintervals. And that means that we are going to be getting close to, we're going to be approaching 0 error. Because if the width of the interval is approaching 0, if the subinterval is approaching 0, then we're not going to get the error from the Riemann sum. And so by adding up all of these infinitely many tiny rectangle areas, we're going to get the exact area under the curve f of x. And we are going to use a special notation for this limit. this limit of the Riemann sum. This part right here is the Riemann sum. This is the Riemann sum. Now when we take the limit as n approaches infinity, because this is the limiting value of that Riemann sum, then we're going to use a new notation for that. All of this part right here, the limit as n approaches infinity, sum from k equals 1 to n, is going to be replaced with a different symbol to represent this summation. And the symbol we're going to use there is like just think of an elongated S. We're just going to elongate that S like that, because it is representing a sum. And we're going to indicate the interval on which we are working by writing the left endpoint at the bottom and the right endpoint at the top. So these are called our upper and lower limits of integration. So this is the lower limit of integration, but you'll also often hear me just call it the lower bound. And then we have B is the upper limit of integration, or the upper bound. Now this part right here, let's talk about that next. Delta x, think of delta as the Greek letter D, then it's easy to see that we're just replacing delta x with dx. The delta x gets replaced with dx. And remember what delta x represents. Delta x is the width of each rectangle in our Riemann sum. Okay, then we have the f of x sub k, which we're just going to write as f of x. Because we have sort of hidden this sigma notation where k is going from 1 to n, we don't need the k here. That's going to be taken care of in the integration symbol, that elongated S-shaped symbol. Okay, so this is how we're going to translate back and forth between integral notation and the Riemann sum notation, or sigma notation. Here's an example with an actual function. We have the graph on the right. This is the graph of f of x equals x squared plus 2. And we want to represent the area between the curve and the x-axis on the interval from 0 to 5. So first we're going to set up this as a Riemann sum. We're going to use the right Riemann sum. And so the interval goes from 0 to 5. I'm just going to indicate my interval here goes from 0 to 5. So A is 0, B is 5. The width of my interval is 5. And so the width of each subinterval is the width of the entire interval over n, right? That's what we said back here, that the width of the subinterval is b minus a over n. So in our example, b minus a is 5. 5 over n is this term right here. That is the width of the interval. That's our delta x. And then when we translate to integral notation, that turns into the dx. So you can see that those are colored in blue. So you can see how one is transforming into another. Now in this notation here, we're not seeing very clearly that the interval goes from 0 to 5. It's more clear in the integral notation down here, where we have the lower and upper limits very clearly stated there, that our interval goes from 0 to 5. The next part that we have here, we want to look at this 5k over n. So I'm going to write down, first of all, that delta x equals 5 over n. And now we can say that this 5k over n, that term that I have in green there, is equal to just k times delta x. That's k times delta x. And remember that a plus k times delta x equals x sub k. So x sub k equals a plus the 5k over n here, and our a value is 0. So that's just going to drop out. So we have x sub k equals 5k over n. Okay, so this didn't change from this step to this step, but when we got to this step, it just turned into an x. It turned into an x. Remember, we can drop the subscript k. when we're going to integral notation. So it just all became an x. So this x value is being squared and then plus 2. So x squared plus 2 is the function. Then all of this turns into that integral symbol right here. All of that turns into the integral symbol. Let's look at this example. We're given an integral. So we have definite integral notation here, and we want to match that with the appropriate Riemann sum. So the first thing I recommend is writing down what your delta x is equal to. Delta x is determined by the difference between where the overall interval starts and where it ends, so the b minus a divided by n. In this case, our interval goes from 3 to 5. I'm going to write that down, 3 to 5. That's our a and our b. Okay, so delta x equals 2. I'll go ahead and write 5 minus 3 to be clear. It's 5 minus 3 over n. So it's 2 over n. That's the delta x. And that means that my x sub k equals my starting point, which is 3. The interval starts at x equals 3. So that's the a value, a plus, and then k times delta x. So you can write k times 2 over n like this, but normally we see that the 2 and the k are multiplied together when we see this in a multiple choice type question. The k and the 2 are usually multiplied together. So we'll write 2k over n. That's what is going to take the place of the x. So let me highlight that. All of this right here is going to replace the x from the integral notation. So we'll make a substitution. We've got 3 plus 2k over n. That's the x. It's raised to the power 4. Then the dx right here is the 2 over n. Right? We said that here. That's the 2 over n. The dx is delta x, the 2 over n. Then for the rest of it, we just have the sum from k equals 1 to n, and then the limit as n approaches infinity. So right away, by figuring out that delta x is 2 over n, we can eliminate this answer and this answer, because we know that we have to multiply by delta x. So there's the delta x part of the problem. And it doesn't always have to be at the end because multiplication is commutative. So it's very possible that sometimes they'll put that delta x in front. And you just want to be on the lookout for where's the delta x. So we can eliminate a and c because there the delta x is only 1 over n, not 2 over n. In the other two answer choices, here's the delta x, here and here. So either one of these could be correct. Now we have to look at, the only difference is the x value, how they're defining that x value. And if our delta x is 2 over n, then we need k times 2 over n. K times 2 over n, like we have right here. So it's got to be d. In this next example, we have the definite integral from 2 to 5 of 4 minus 2x dx. And so again, I would recommend we start by writing down what is delta x. Delta x is the width of the overall interval. We're going from 2 to 5, so 5 minus 2, and then divide that by n. So it's 3 over n is our delta x this time, which is going to replace the dx, 3 over n. So looking at my answer choices, here's where they have that delta x at the end right here. We want the one that says 3 over n. So it's either going to be c or d. We can rule out a and b. It's not a, not b. Now let's get the expression for x. So x sub k, it's going to be our starting value. The interval starts at 2 plus, and then k times delta x. So k times this value right here. So 3k over n. That is what is going to replace the x from the integral notation right here. All of that is going to replace that x. So it's going to be 4 minus 2, and then in parentheses we make this substitution. 4 minus 2 times 2 plus 3k over n. All of that gets multiplied by the dx, which is 3 over n, and then we can fill in the sum from k equals 1 to n and limit as n approaches infinity. So that is choice D again. Let's look at some properties of summation. Number 1, we are summing c from k equals 1 to n. So we let k equal 1, then we let k equal 2, then we let k equal 3, and so on. Not let c equal 1, 2, 3, we let k equal, but there is no k. So when we write this out, we end up getting c plus c plus c plus c. No matter what the value of k is, the term is just equal to c plus dot, dot, dot. So how many times are we doing that? Well, we're doing that n times. We're starting with k equals 1. Remember, k is a counter. K is 1, then k is 2, then k is 3, and we stop when we get to k is n. So by the time we get to k equals n, we've repeated this process n times. And by this process, I mean we just keep adding c. So it's equal to c times n. C times n, where c is a constant here. Property number 2, we have c as a constant multiple. So if I were going to work this out the long way, starting with k equals 1, it would be c times a sub 1. When k equals 2, for the next term, we get c times a sub 2, then c times a sub 3, and so on. Each of the terms has c as a constant multiple, so you can factor c out from each of the terms, and then we can actually factor it completely out of the summation. So the property allows us to factor that constant multiple out of the summation altogether. So we're going to get c times the sum a sub k. K equals 1 to n. And our third property here, if we have multiple terms that are just being added or subtracted, we can separate this into multiple summations. So we can take the sum of a sub k from k equals 1 to n plus or minus the sum from k equals 1 to n of b sub k. So we can split this up from a single summation into multiple summations. Now we also have these summation formulas. We can prove these formulas using mathematical induction, but for now we're just going to use them as is. So if you are summing k from k equals 1 to n, that sum is going to equal n times n plus 1 over 2. If you're summing k squared from k equals 1 to n, it's going to equal n times n plus 1 times 2n plus 1 over 6. And the sum of the first n cubes is n squared times n plus 1 squared over 4. We are going to use these summation properties to evaluate this definite integral. The function is 3x plus 1. We're working on the interval from 3 to 5, and we want to evaluate this, which is going to give us the exact area under the curve on this interval. So the first thing we're going to do is translate this into that Riemann sum form. Our delta x, well, our interval goes from 3 to 5. So 5 minus 3 over n, or 2 over n. Our x value will be our starting value, which here is 3, plus k times delta x. So k times 2 over n. And then once we know those two things, it's very easy to translate this. So it's limit n approaches infinity, the sum from k equals 1 to n, and then we simply substitute this in for x. So 3 times 3 plus 2k over n plus 1. And then we substitute this in for the dx, so times 2 over n. Now we're going to evaluate this. We're going to use properties of summation to help us evaluate that. So the first thing I'm going to do is just simplify by distributing this 3 here. I'll do this in small steps. So that'll be the first thing. So 3 times 3. 3 times 2k over n plus 1, and then times 2 over n. Okay, so I'm still simplifying. I'm going to go ahead and add the 9 and the 1 to get 10, and then I'm going to distribute the 2 over n. So limit as n approaches infinity, sum k equals 1 to n. The 10 times the 2 over n is going to give me 20 over n. 6k over n times 2 over n will be 12k over n squared. Now we're going to wait on the limit and simplify the summation first using those properties. And this summation, it has k's in it and n's in it, and they're not both treated as variables. What is treated as the variable is the k. That's the thing that's changing from starting with k equals 1, then k equals 2, then k equals 3, then k equals 4, all the way up to k equals n. K is the thing that's changing. N is not changing, n is fixed. Okay, so we're treating n as a constant here. If n is a constant, then 20 over n is a constant. It's a constant multiple. And so we saw this, I'm going to go back. This property number 2 says that we can take a constant multiple and factor it out of the summation. This constant multiple right here can be factored all the way out of the summation. Now you cannot factor out a variable, but you can factor out a constant multiple. So I'm not even thinking about the limit yet, still simplifying the summation. 20 over n is a constant multiple, it's going to come out. I'm also going to use my sum and difference property. Let me go ahead and do an extra step here. This was property number 3, where we can separate this into two limits. So we have the sum from k equals 1 to n of 20 over n plus the sum from k equals 1 to n of 12k over n squared. Okay, so I used property number 3 to separate that into two different summations. And then the 20 over n in the first summation is a constant multiple. I'm factoring that out. Now, when you factor it out, what's left behind? It's not 0, it's not nothing. The summation doesn't disappear. We left a 1 behind. We factored 20 over n out. That leaves a 1 behind. Then in the next summation, we also have a constant multiple. I will highlight that in yellow. 12 over n squared is all a constant multiple. Remember, n is being treated as a constant here. 12 over n squared is a constant multiple, so I can factor that out, leaving behind, this time, a k. Okay, now for this first summation, still simplifying the summations, we're going to use that first property that says if you have a constant, if you're summing a constant from 1 to n, it's just equal to the constant times n. That was property number 1. So this is just equal to n, 1 times n. Okay, all of this I'll highlight. All of this right here is equal to n plus 12 over n squared. Now this, we're going to use one of those formulas. We have the sum from k equals 1 to n of k. Let's go back. The sum from k equals 1 to n of k is equal to n times n plus 1 over 2. So let's make that substitution. N times n plus 1 over 2. N times n plus 1 over 2. Now notice we no longer have summations in this expression, which is good. Now we're ready to take the limit. So the limit of 20 over n times n, these n's actually reduce to just 1, right? N divided by n is 1. So it's the limit of 20 plus, and the limit of a constant is just the constant, so 20 plus, now it's the limit of 12 over n squared times n plus 1 over 2. And we can use the shortcut where we have degree 2 on top. You have to kind of mentally work out what would the leading term be if you were to expand all of that in the numerator. The leading term would be 12n squared. In the denominator, it's 2n squared. And so the ratio of those coefficients, 12 over 2, is just 6. 6. So the limit is equal to 26. And all of this is equal to this definite integral right here. Now, I would like you to check this using your calculator. So on your TI-84 Plus, you are going to hit the math button, and then number 9. And then what you're going to see on your calculator, if you have the newer operating system, is a template. So you get the integral symbol, then you get a little box to enter your upper and lower limits of integration. Then you get a box where you would enter your function, and then d variable. Okay, so your job is to type in the values of a and b. So this is a 3, and this is a 5, and then you type in your function, which is 3x plus 1, 3x plus 1, and then here you're just going to type in the x. Just hit the variable key to generate x, and let's make sure we get 26 as the answer. So it's a great way to check your work with a definite integral. Math 9 on the graphing calculator. Let's do another example. This is the one that we're trying to evaluate now, so we will be able to use the graphing calculator to check the answer, or even get the answer right now if you want to. But we're going to work it out the long way using the limiting value of the Riemann sum. So the first thing we're going to figure out here is what is our delta x? And our interval goes from 0 to 4. That's our a value of 0, our b value of 4. So the delta x is that width of the interval, the b minus a, over n. So it's 4 over n. That's our delta x. Then our x value, it's your starting value, the a value, plus k times the delta x. So 4k over n. Now we don't need to write 0 plus. We can just say that x sub k is 4k over n. Okay, so now we are going to substitute that in for the x, and we're going to substitute the delta x in for the dx. So it's going to be 2 times 4k over n squared plus 3. All of that needs to be in parentheses. That gets multiplied by dx, so 4 over n. And then we have the sum, k equals 1 to n, and the limit as n approaches infinity. Now, before we take the limit, we're going to simplify this algebraically. Okay, so I want to simplify this term here, and then I also want to distribute the 4 over n. So limit of the sum, k equals 1 to n, 4k squared, 16k squared times 2 is 32k squared over n squared, plus 3 times 4 over n. Now we're going to distribute the 4 over n. So 32 times 4, 128, over n cubed times k squared plus 12 over n. So let's separate this into two summations. We've got, and at the same time, I'm going to go ahead and factor out the constant multiples. So this is a constant multiple, this is a constant multiple. 128 over n cubed times the sum of k squared, k equals 1 to n, plus 12 over n times the sum, k equals 1 to n, of 1. And then we'll go back to our properties and formulas here. We need the formula for the sum of squares. And that is this one right here. So it's n times n plus 1 times 2n plus 1 over 6. So limit n approaches infinity, 128 over n cubed times n plus 1 times 2n plus 1 over 6 plus 12 over n. And then if you remember, this right here is just equal to n times n. Okay, so that's going to cancel out. And for the limit, I'm using my shortcut rule. I've got degree 3 on top, degree 3 on bottom. So work out what that leading term would be in the numerator. It would be 128 times n times 2n. So 256 n cubed is the leading term in the numerator, and 6n cubed is the leading term in the denominator. So 256 over 6 plus 12. Or, let's see, 128 over 3 plus 36 over 3 is going to give us 164 over 3. Okay, then we can use math 9. To verify our answer, this is the definite integral you would enter into your calculator, and we should get that same result. We have one last example. You might want to pause the video here and try and work it out on your own, and then come back and we can go through it together. So I would start by writing down the delta x. The interval goes from 2 to 5, so delta x, 3 over n. And then x sub k is going to be your starting value, your a value of 2, plus k times your delta x, so 3k over n. Okay, so we're going to now substitute in for x and in for dx. So we have two different terms where we're going to substitute in for x. So we'll have the limit as n approaches infinity, sum k equals 1 to n. And then our function here, 8 times the x value. So we're replacing x with 2 plus 3k over n minus the x squared. So 2 plus 3k over n squared. All of that times the dx, so times 3 over n. Okay, we have a lot of simplifying to do before we take the limit. Okay, we have 8 times 2 is 16, and then 24k over n minus, and I'm going to FOIL this out, so 2 times 2 is 4, and then 2 times 3k over n, and double that is 12k over n, but we're subtracting, so minus 12k over n, and then 9k squared over n squared, and we're subtracting 9k squared over n squared. And then we still need to multiply by 3 over n. We also have some like terms here. We've got the 16 and the minus 4, and then this term and this term can be combined as well. So let me combine those like terms first, and then I will distribute 3 over n. (16 minus 4 is 12. 24 minus 12 is 12. Minus 9k squared over n squared times 3 over n. (12 times 3, so 36 over n, plus 36k over n squared, minus 27k squared over n cubed. Okay, so here we're going to separate this into 3 different summations and then apply some of our summation properties and formulas. So the first one, I'm going to go ahead and factor out these constant multiples in one go. So that's a constant multiple, that's a constant multiple, that's a constant multiple. The k is the variable here. So we've got 36 over n times the sum of 1 from k equals 1 to n, and that's going to equal n. Then 36 over n squared times the sum of k from k equals 1 to n, and that, look at the formula, n times n plus 1 over 2, minus 27 over n cubed times the formula for k squared, n times n plus 1 times 2n plus 1 over 6. And then we're ready to take the limit. So we get 36 plus, now here the 36 over 2 is the ratio of the leading coefficients, so 18. And then on the next one we've got 27 times 2 as the leading coefficient in the numerator, and 6 as the leading coefficient in the denominator. So that's going to leave us with a 9, minus 9. So our final answer, 45. And again, you can check that using Math 9 on your graphing calculator and entering this definite integral right here. That concludes our lesson for this time. Next up, we're going to talk about the fundamental theorem of calculus. See you then.